Very often we will have surfaces or materials that have small scale physical detail on them that we wish to replicate in order to make them look more realistic. This is going to be things like pores on skin or grain in wood, stuff like that. Replicating this in geometry via modelling is going to be exceedingly difficult, A, because of the poly count you would need, and B, because of the amount of time that would be required to create all of that additional detail. As such, we need an alternative way to put this detail into our model, and this is where we come to bumps, normals and displacement maps. You'll see that we have a couple of inputs for them. For instance, on the main surface channel here we have a normal, bump and displacement input, whereas on the material nodes we have a normal and bump input. Of course, anything that you plug into the surface destination node here is per surface, and so you can change out the material and stuff plugged in there remains constant. Whereas of course if you're plugging normal and bump maps into the material itself, then as you change materials those will change along with it. The main difference in hooking them up, let me just for instance hook up the bump map that we have here for starters, you can see a little bump effect taking place there, is that when we hook to the surface input then we need to use the amplitude setting in the bump map itself if we want to make the bump map get stronger or weaker. Changing the bump height in the actual surface itself will have no effect whatsoever. Whereas if we connect the map to the surface, then both the amplitude setting in the map itself and the height setting in the material will have an effect on the eventual outcome. Displacement maps don't have a height control here, as you can see they're just a scalar input. Of course you could always use something like an add or a multiply node or some such here to modify the displacement strength, but ordinarily you use the surface displacement feature here on the actual object properties modify in the deform stack, the displacement stack, and you modify the strength simply by putting in a distance here. You'll also notice here that the bump map, which is just a grayscale black and white map, I have here in a regular image node, whereas normal maps have their own specific normal map node, which is basically the same as an image node, but it is specifically for handling normal map. Also notice the preview of the normal map here. It is this bluey purpley colour. We can see it in close up here. We have this blue tinted normal map. Normal maps come in two varieties. There is this blue kind, which we see here and is increasingly common. This is known as a tangent space normal map. Here the colours represent vectors from the mesh tangent. The other format you might see them in is like this, where they have this sort of RGB coloration to them. This is an object space normal map where the colours represent vectors in the object space itself. Both are in use in different places, however Lightwave only uses the tangent space normal map. So if you have this kind of normal map, you'll get weird results in Lightwave. What you want is a normal map of the blue variety. The other thing to take note of is the colour space of these maps. Very often these will just be sRGB 8-bit images. They won't be float or EXR, though occasionally you may get maps supplied in that format. However, normal maps, to work properly, will always be written out in linear colour space. When you use ZBrush or 3D Code or some such and it writes out a normal map, even though it will save it in an 8-bit file, or can save it in an 8-bit file, it will not save it in sRGB colour space because it is a map of vectors. As such, these maps don't need to be colour corrected or gamma corrected, and they should not be so. As a result, when you load a normal map in, you always want to make sure that it has its individual colour space set to linear. The same may be true of bump maps. These are usually grayscale maps, even if they're stored as RGB rather than actual grayscale file. However, because they are simple scalars, all that colour correction will do on them is just shift their contrast. So if I put my bump back on here, and we see that effect there, you can see the difference when I switch it to sRGB. and it simply comes out with a different strength profile. It's not that the entire map has gotten weaker, which is what it appears, it's simply that the difference in contrast between white and black has gotten different, and that just changes the appearance of the map. As such, which is correct for a given bump map, linear or sRGB, there isn't really a correct answer. Of course, if the map was specifically created to be linear or saved in linear colour space, then clearly to get the correct result from wherever the map has come, you would want it to be linear. But all changing the setting for on a bump map will do is simply alter the contrast and therefore just affect the relative strength of it, and so it can really be either way to taste. The same is also true of displacement maps, which will again simply be in a grayscale format here. They're a height map, depicting high and low areas as a scale of white through black. Again, very often, some applications, ZBrush and so on, when you save a displacement map out of that, it will be saved as a linear map, so you should change it to linear, or ensure that it has come in as linear. The point is, with bump maps and displacements, having the colour space set wrong will only give you a different look. With normal maps, having the colour space set wrong will actually break the effect of the map in many instances and cause it to render incorrectly. Something else that's important to get right with normal maps is their direction. We say, that because normal maps are RGB like this, they can express vectors rather than just high-low. And that's true, but what they're really doing is they're expressing high-low as seen from different angles, specifically the angles of X, Y, and Z. They are basically like a triple bump, what the bump looks like when illuminated from either the X, Y, or Z direction. The problem that you run up against is that not all 3D apps use exactly the same order of coordinates. For instance, in most applications, Y is up. In 3ds Max, Z is up. In most 3D applications, Z is front to back, forwards and backwards, and it is such in Lightwave, but in Lightwave it is the opposite way round to most other applications. So what in many applications is the positive Z-axis, in Lightwave is the negative Z-axis, and vice versa. And this can sometimes cause the X-axis to appear misrepresented, depending on whether the X-axis is just taken to be a certain direction or taken to be to the left or right of the positive Z. Because of this, when a normal map is created in one application, it is created, the XYZ components are created from the XYZ view of that application. And if that's not matched, when you transfer the normal map into another application, it can make things look weird. For instance, this normal map texture that we can see here, and it's just these nice, simple, soft bumps. But if we look at how they're rendering here, well, we've got this sphere light, and we see the, highlight on this outer edge here and the same here. So, these bumps look as if they're raised up, okay? They look like outies. Same down here, on this side of the sphere, this view, of course, being from the top. But if we look at these guys on the side, then we see that their outermost part is getting highlight there, whereas their inner edge is in shadow. These guys look like innies, and the same over here. And if we look at it here in perspective view, we see something of a mixed bag. Some of them look like innies, some like outies, some look like they're sort of tilted, up on one side and down on the other. It doesn't look correct at all. And this is all to do with a mismatched coordinate axis. As such, if we bring up the normal map, then you can see that some of the options here are invert X, Y, and Z. If we turn on invert X, then now we see, look, we're getting the highlight on the outer edge here of all of these bumps. And we see here the same thing in perspective view. Their highlights and their shadows are all consistent with one another, given the position of the light. In this mode, they all look like outies. They look like bumps up on the surface. However, because of this behaviour, we can treat them another way. If we turn off invert X and instead turn on invert Y, then once again, they all look correct given the position of the light, but now they look like depressions in to the surface rather than lumps coming out of it. If we turn on invert X and Y, then we're back to something weird again. And if we turn on invert Z instead, then we get something that's completely wrong. So you might well find, especially when picking up normal maps that have been created in some other package, that you need to throw some of these switches here. Most commonly it will be the X, but occasionally it will be the Y. And this will ensure that they render correctly, and also, in many instances, give you the option to make the normal bump appear to be raised up or depressed in. And of course, much of the time you want to get that the right way round to match with the way that the normal map has been created for a given object or surface. So with those details out of the way, then what do our bump and normal maps do? Well, as you can see, they just create this fine scale detail on the surface. Here we see the effect of a bump map, and if we plug in instead the normal map, then we can see the effect of that. As it happens, both of these maps are depicting the same surface. You can see here the little fine details in the bump map, and the normal map you can see largely exactly the same pattern of detail. The difference is simply that bump maps, being black and white, being grayscale, contain up-down information only, high or low. Normal maps, being in RGB colour, represent vectors, and so they can represent surface bump detail in more than one direction. Due to this, normal maps are an awful lot like bump maps. They just have more information and can cause you to get finer grade detail, as we see here, compared to the bump map. Beyond that, though, they are still both cheats. If we plug in the bump again, and we can turn this up as high as we like. Let's turn up, I don't know, 4,000%, shall we? There we go. Really, really very bumpy. However, whilst it looks bumpy on the front surface here, if you look at the edges of this sphere, then you'll see that they are still perfectly clean. There is no actual bump taking place at the edges. This is nothing but a fake effect. It is a shading trick, nothing more. And that is true both for bump maps and normal map. Displacement is different, and if we take the luma here from this grayscale image, which is a scalar, and we plug that into displacement, then, well, we see that the ball gets a little different. Can you notice? You get a little bit of lumpiness occurring. There it is smooth, plug in displacement, and there it is a little bit lumpy, kind of different. What a displacement map does is it actually displaces the geometry itself, as if you had modelled all of this small scale detail in. The trick with that, of course, is that you require enough polygonal detail to be able to show this displacement and this small scale detail. As such, even though we've got surface displacement active and we've got a distance here, and you can see the displacement turning on and off there as I toggle this control, what we don't have are enough polygons to show this tiny little level of detail. If we just plug that into colour swiftly, then of course you can see, just as when we saw the bump map alone connected, just how small scale these details really are. So what we need to do is to have a higher poly object, which of course in this case we're doing through subdivision. If we turn up the subdivision levels a lot, like let's say 32, then we get tons of polygons, and the result of that, of course, is that there is now sufficient geometry for our small scale detail to start pushing the geometry out. And you can notice from the displacement that the edges of our sphere are becoming lumpy and bumpy. It is no longer just a simple faked shading effect. It's an actual geometric effect. The one thing that you might find with displacement maps, and again it depends on how the displacement map has been created and the intention behind it, is that sometimes black represents no displacement, and the purpose of the displacement map is purely to push geometry outward. Some other displacement maps, and ZBrush is the classic example, take 50% grey as flat, and anything that goes towards black is intended to push the mesh in, and anything that goes towards white is intended to push the mesh out. Ordinarily, just hooking up as I have here, the displacement is a scalar. So when you input black, which is equal to 0, that means no displacement. We can see this very easily if I get a constant colour here. Let us set it to be black. We'll get a colour to scalar node, plug that in and choose to take from it the luma, or the brightness. We plug that into displacement and nothing happens. But of course, if we set this to white, then the sphere bloats. How much by? Well, 1, which is equal to white, times the 20 millimeters that we put into the surface displacement setting in the object properties. As such, if you have a displacement map that is intended to be flat at 50% grey, go inwards towards black and out towards white, then you'll want to take a math scalar subtract node like this, put your luma in, and simply from it subtract 0.5 or 1/2. Thus 50% grey is no longer 50% displacement, it's now 0 displacement. Going towards black is negative displacement and going towards white is positive displacement. And when you plug that in, your displacement map will then push some of the geometry in and some of the geometry out. Of course, you can stack these all together, so you can use a displacement map, plus of course have a normal map going on, which gives you additional shading on top. Plus, of course, you can still have some measure of bump if you're wanting that as well. Stacking these effects together to try and get the best possible look to your surface. And so simply, there we have it. That is bump, normal, and displacement mapping in Lightwave, the various places where you connect them up, the options for them, and how to treat them properly and differently, of course, to get the correct results for your given surface or material.